Morning, everyone. Welcome back. So today, I think I still need to give the reason why last time we talked about non-convex optimization, and the last algorithm we talked about was Frank-Wolf, and we didn't show why Frank-Wolf didn't work for the non-convex setting if you choose the prefix subsize 2 over k plus 1. Over here. So the subsize alpha k is 2 over k plus 2. So the key inequality we use to show convergence was this one. X plus this is for one iteration. We have this recursive formula. And the way we show convergence for non-convex setting is to show this sk, s of x goes to 0. So let's see, we need to have, and in this case, we choose this t to be alpha k, t something between 0 and 1. And if you choose the first choice of the subsize, it's alpha k. So we need to sum this inequality and then use a time scope sum here. So you're gonna have summation alpha I s of xi. So suppose this alpha k is, we choose alpha k like 1 over k. Right? This is roughly on the order of 1 over k. And on this side, summation of 1 over k will give you 1 k. Right? And here, this summation of alpha k of I square is summation 1 over I square. This is roughly 1 over k. Right? Then what you have on this side is minimum s of xi, I from 0 to k minus 1. Right, because phi of xk is always lower bounded by phi star. You assume it's bounded from below, divided by log k. Here we can use the diameter to bound this difference, right? So we have LD square. And summation of alpha I square is 1 over k. So here we have k times log k. Right, this is the final result we are going to have. But the drawback here is this, the rate of this one goes to 0, goes to infinity, it's too slow. Log k is not desired. So that's why we will never use this one for non-convex setting. Right? Because ideally this will be k to some, at least this is k to some power alpha. Alpha is can be slow, but often needs to be maybe lower bounded by some small constant, but cannot be too slow, right? This long case too slow. So that's the reason why we just present the adaptive subsizes and also the exact minimization, the two subsize rules. Okay, so let's go back to stochastic optimization. I want to start the discussion from a different problem, which is the sampling problem. Basically, you are given a probability density function. This can be viewed as a PDF. It's P0 of x. And you can always write the density as something proportional to, in this form, exponential of negative f of x. And this f is the negative log density. Okay, for example, this is a Gaussian distribution. F here is a quadratic function. Right? If it's a exponential distribution, then this is just a linear in x. Okay, these are some simple examples, but you can always rewrite your PDF into this form up to a constant, right? Some normalization constant. And so we want to, suppose you know this density function, and you want to sample a point from this distribution, which follows this distribution, right? This problem can be written as a minimization, as an optimization problem in the probability space. So this can be written as minimizing the scale divergence between the target distribution and some proposal distribution. And this distribution is just in the space of all probability distributions. Here it just means the second moment is bounded. This is the usual regularity condition. And scale divergence in the continuous setting. So in the discrete setting, we have seen this already. We use it as a Brakman divergence in the mirror descent, right? Remember, we choose the descent generating function as negative entropy, right? We will write it as xi log xi. This is the negative entropy. And here, we just write it, and then the Brakman divergence for this W. Right, this is the discrete setting, but in the continuous setting, we are going to change this summation to be an integral. Okay, so this is the extension from discrete to continuous setting. So this is a functional of P. P is a density. P is already a function, so this is a function of a function. It's called a functional, right? And the KL divergence here shares the same properties as the one in the discrete setting. First, it is not symmetric. Okay, so this is not a metric. It's not symmetric, and also it's always non-negative for any different two pairs and any different pairs, right? Mu and nu. And it is zero if and only if mu is the same as nu. So here, this scale divergence is always non-negative, and you can achieve the minimum when this P really becomes the target distribution P0. Okay, so our goal is to choose a P in the space of probabilities such that this P will be close enough to the P0, and then then it means you can sample from this P, whatever you propose here. You have ability to sample from here. When P is close enough to P0, your sample will be close enough to the real sample from the true distribution, right? That's the goal here. So we can rewrite this sampling problem as an optimization problem. And we can even further simplify this expression by parameterize the distribution. Because here, P and P0, they are not parameterized at all. You have like infinite dimensional object. You are minimizing an infinite dimensional function. So, well, usually we just minimize in a finite dimension, right? Like what we have done so far. We just minimize in Rn space. So we can parameterize the distribution so that we can minimize in finite dimension space. So let's parameterize so first switch P0 and P, right? Even if we switch them, it's still always negative and 0 when P becomes P0. Right, so we first switch them. Let's minimize P0 given P. And then we parameterize both of them. So we parameterize P0 as P theta 0. We parameterize P as P theta. So if theta 0, a vector in Rn space is given, then we can determine P theta 0. It happens to, same thing happens to P theta. If theta is given, then you can parameterize P theta. You know everything about P theta. You can do sampling and everything, statistical inference on it. Right, so then the problem boils down to determine a vector theta that is close enough to theta 0. Right, so this becomes a finite dimension optimization. But we first still work with the distribution directly.
Yes, the reason that we don't sample from P theta 0 is that we don't know it exactly. Am I correct? The distribution P0.
You know P theta 0, you know this distribution, but directly sampling from it is not easy. How can you sample from this? Even if I tell you what F is, this is not easy to sample from.
It requires, I think,
F can be very nasty. For example, F can be L2 norm plus maybe some L over 2, 1 norm, right? Can also be minus. Can be, even if you know the form, but it's not easy to do. You still need an algorithm to sample from it.
so we try to find distributions that we can sample from them, similar to that one, that F. And
Yes, in the end, it's similar to optimization. You need to have a sequence. In optimization, what you have is a sequence of points, right? And in the end, you know when this n is large enough, xn will be close to x star.
Yeah.
Maybe you can measure the difference, or in terms of a function value difference, right? You can show it's close enough. And in sampling, so you begin from some rho 0. And this is your initial, so here you have an initial point in optimization, but in sampling you can start from an initial distribution. This can be something simple like a Gaussian distribution. And then you can evolve along some dynamics so that the distribution will also go along a trajectory. And this, so this is, for example, this follows the gradient descent, for example, right? And this can also follow some dynamics called Langevin dynamic. And in the end, if n is large enough, rho n will be close enough to the target distribution P0. It's also measured in maybe some metric or divergence. For example, KL divergence is one way to measure the differences between the two, right? And also you can measure in some other functionals. You can measure the F divergence or something else. But there's always a way to measure the convergence of this iterate. The iterate here is the distribution, right? The key difference between the two is this is finite dimensional object, but this is infinite dimensional. And what we do there is to simplify it by parameterize the distribution so that we can still work in finite dimension space. Okay, so let's see with this parameterization, how can we simplify this object here? First, we use the definition of KL divergence. Here, this is the distribution for RD space, because here X is in the space of RD, and here theta is in the space Rn. They're different, right? This is the way you parameterize the distribution, but this is, so you want to take a sample. The sample is actually X, it's in RD space. There are two different dimensions. But here we are just rewriting the KL divergence using its definition. From here to here, we just press this log of a ratio as log of A minus log B, right? And then because this minimization is for P theta, so this is a constant. You can take it out from the minimization. And then if you put it after the minus sign, you need to change mean to max. From here to here, this part keeps the same, and here we just write this integral as an expectation. Right? Because here, even if here is maximization over distributions, but it's really just finite dimension maximization. So here we are just maximizing over theta. Theta is in its space. This is capital theta. But for example, this can also, there's no constraint. This can also be written as Rn, right? Theta is from Rn. And here, the randomness here is in Z. and Z is Z follows this distribution because Z is from here. This is the density that Z needs to satisfy the PDF. So Z is from P set at 0. And so if you write this expectation as integral, you first need to have the density for this Z, right? That's no, this is P, should be P theta. I should switch theta. Oh, yeah, here, this line, right? Here's, yeah, P set 0. Right, this is right. So this is the density for Z. So here's P set at 0, and this is the object we are integrating, right? So this is what's inside the expectation. And now, by parameterization, we turn this infinite dimensional minimization to be this finite dimension maximization problem. So in the end, this sampling problem boils down to this maximization, right? Which is just this part here, just rewrite here. And this falls into the general stochastic optimization formulation. So in general, we want to solve this problem. This is what we are familiar with. So here, for simplicity, I just write the maximization problem here. And what we want to maximize is what we have seen so many times is composite optimization problem. Here, H is again closed convex, F is also convex, but F has more structure now because F is an expectation of some stochastic function. Here, this capital F function depends on two input. One is the decision variable X, the other is the randomness C here. And this is expectation taken over C, so this F is deterministic, but the capital F is random, it's stochastic. So here, the theta is like the randomness C over there, right? This theta is like C, and no, sorry. Theta is the decision variable. Theta is X. Theta is what's in Rn. So theta is X there. And the Z is like the C. Z is the C. The capital function, the function capital F is this log P theta 0, P theta. This is your, actually here, this theta is X, Z is C. So the whole thing, this is your Fx C, right? And this is expectation over C, which is Z here in this case. This is a special case of that problem, right? So this is we turn this sampling problem with parameterization into a stochastic optimization problem.
When we say that we want to minimize that KL divergence over the distributions that are included in that set with d dimensions, we are saying that exactly we have a bunch of, for example, Gaussians. We want to find the theta that are included in the Gaussian sets with d dimensions. Am I correct?
Yeah, but this is larger than Gaussian. This is everything.
Yeah, everything. I just made an example.
Yes. But we don't restrict the class of distributions. If you are only minimizing over Gaussian, that becomes variational inference. It's a different problem, but related. Here, there's no constraint. This problem is actually, what we do here is indeed MLE, maximum likelihood estimation. because in maximum likelihood estimation, we usually parameterize the distribution. And the way we solve this, here is the log likelihood of the density, right? And we want to maximize the likelihood. And the way we really solve it in MLE is by taking samples. We take samples of the Z. So we first take a large number of samples. So we first take n samples from this distribution p theta 0. Right? This is the observation that you can really observe, right? The samples from this true distribution, but you don't know the distribution, you just observe the samples. And then with these samples, we take a sample average, right? Here we just plug in the ZI, the sample you observed, and then take the normal average. And then we try to minimize this function with respect to theta. Right? This is like an approximation to this expectation. If the number of sample is large enough, then this average will be close enough to that expectation. Right? This is usually we solve MLE. And now this problem, it reduces from this stochastic optimization to a deterministic optimization because you take the samples. Randomness is in the samples, right? And then you can use your favorite deterministic optimization algorithm to solve it. So this is the SAA approach we mentioned many times. Sample average approximation. You first take samples and then you take average. It serves as an approximation to the stochastic optimization problem. This is called SAA. And so because we first take samples and then optimize, so then this becomes an offline approach. Right, because the stochasticity is separated from optimization. Right, so after you take samples, it becomes deterministic. So this is an offline approach. We can also do an online approach that is SA. This is stochastic approximation. For example, in SGD, stochastic gradient descent, your xk plus 1. So this is an iterative method. So here we just do a gradient descent step, but we replace the gradient at xk by a stochastic gradient. So this object here serves as a gradient, but it depends on the randomness, the ck. It serves like a subgradient to this function. Right? So it depends both which point you're at and also the randomness you take at this step. Depends on the ck. So if ck is different, then the subgradient is different. So this is because here optimization and the randomness, they happen at the same time. So this is an online approach. first take a sample and then optimize. The next iteration, you take a ck plus 1 at the point xk plus 1, and then solve for the next point xk plus 2. Right, so you mix the two steps together. But here, you separate the two steps. You take samples first and then optimize. But here, sample and then optimize, sample, optimize, do it in alternative steps. Right? So these are two typical approaches to solve stochastic optimization. And here, so let's first talk about the first approach, SA. Intuitively, if you take a large number of samples, then the SAA will be close enough to the stochastic optimization problem. But can we quantitatively say how large the number of samples should be? Can you give something like a convergence rate? How fast your approximation will converge to this true objective here? So we need the following technical results. The first inequality we need is a concentration result. This is the Hoyt-Footing inequality. Suppose x is a random variable. This is just a random variable, not a vector, just in R. And x is supported on a bounded domain from A to B. And we take n samples, n IID samples, independent and identically distributed samples from x. These are x1 to xn. And then this inequality holds for NA non-negative t out of t written up to 0. So this is an estimation of the average to its mean. This is pretty much like our goal there, right? I want to estimate how far my SAA will be different from the expected function, right? So this is my SAA, this is my SO. I want to measure how different they are. So the probability that the difference in absolute value is larger than or equal to some given tolerance threshold t, this will be less than or equal to exponential to the negative t here, right? If and also this is this part is proportional to n, so It means if you take more samples, if this n gets larger and larger, because it's exponential to the negative, so this will go to zero exponentially fast, right? So this really verifies the claim that if you take more samples, then your SA will be close enough to the SO. But here, this is only valid for one point. But here these are functions. These are for all the theta in the domain, this capital theta. But here this only serves, only works for one point. But we need we need that similar inequality to be valid for all the theta you care about. But here it's only for one point. So we still need another result to make this valid for all the theta in the domain capital theta. I will do this part very quickly, but no proof. You can check the proofs in the lecture notes.
When we say that this expression holds for just one point, we say that for the same level of randomness, this expression will increase or decrease the zeta, the level of randomness.
Yeah, because this is an expectation of just one random variable, but what we have there, so this expectation, it not only depends on c, but also x. If x varies, then this expectation, because it's a function, right? Then the expectation will be different. Right? But there it's only just for one fixed x, where we need all the x in Rn, or that all the theta in the domain capital theta. Right? That's the difference. So we need to somehow turn this. So there are infinitely many point x. We need to turn it to an object with just finitely many x. So with that being said, we need to introduce a definition called epsilon net. So we first define a distance between two sets. A and B are two sets. introduce the notion of an epsilon net of a set. So epsilon net is a subset of A, denoted by A sub epsilon. And this is a set such that the distance between the two sets, A and A epsilon, is always less than to a given tolerance epsilon. And then the covering number of A epsilon, denoted by n of A comma epsilon, this is the minimum cardinality of this set A epsilon. So for example, suppose this line segment is my set A, then I can choose the A epsilon as all discrete points with distance between each point, each pair as large as epsilon, right? Then I can take, so basically I can take all these lattice points and put them in my A epsilon set, right? And in this case, because this is a bounded set, then this A epsilon is finite. I can just take finite number of points, right? Basically, this n epsilon will be approximately the length of A divided by epsilon, right? I can take this many points to cover, right? It's like a covering. I can take this number of points so that A epsilon covers the set A, because all the other points are within a distance of normal than epsilon from the points in my epsilon net, right? So this is a way to somehow turn an infinite many a set with infinite many numbers to a set that another set that is not far away from this A, but with finite number of points. Right. This is a way, so we're going to use this notion in whole-fitting inequality.
Just make a numerical example. I didn't get exactly what.
Just for example, this A is from 0 to 10, and your epsilon is 1. And then you can just take all the integer points, right? 0, 1, 2, 3, up to 10. You just 11 points, right? That's finite number, finite many points. Question?
So just to make sure I understand what the minimum cardinality of A epsilon is, so that's
because you can take more points, right? You can even take the epsilon over 2 points, all the middle points, but they are not necessary.
so in that example, the epsilon net would be just a set of 11 elements.
Yes.
Okay, that makes more sense.
You can take 12, 13, but they are not necessary.
Okay.
the main result for discussing how the approximation of SAA is close to the SO is summarized in this proposition. The first statement is simple. This is just a union bound. Right? So I believe you have seen union bound in many probability courses. But here I just want to, because to prove this, the second statement we are going to use union bound. So let's just recap what it is. For a set of events, each AI is an event. Right? This is a union of events. Capital I here is an index set. So the probability of the union of all the events in this set is normal than the summation of each individual, the probability of each individual event is happening. Right? This is easy to verify. You can just use the basic inequality that P A union B just use this basic inequality, use it repeatedly, right? And you can ignore this one because it's less than or equal to A plus B, PA plus PB. So use it repeatedly, you can prove this union bound. And with this union bound, we can show the second claim here. So let's consider, so in the stochastic optimization setting, this view is going to be the set of the domain view X. And here, let's just view this set X as domain of H. Right? That's where our X is in. Usually we assume it's in domain of H. Maybe do, for example, proximal gradient or accelerated gradient. We just use domain of H as this capital X, right? And so let's consider an epsilon net of this set X. Let's call it X epsilon. And then with union bound, we can show this inequality. So this cardinality, this index set I here is going to be X epsilon, the epsilon net. All the X in the set is like an index, right? So then, let's see.
If this X epsilon is uncountable, can you sum it?
Here we will assume, okay, I think I forgot to say, so in the lecture notes I make it formal, we need to assume domain of H is bounded.
Okay.
We need to assume it's bounded, because when it's bounded, it's like this A is bounded, right? I said, when A is bounded, then the carbon number is finite. So this is the key to turn an infinite many object to be something finite many, right? We need to assume domain of H is bounded. Okay, so assume domain of H is bounded, then let's see. Yeah, this xi here, x epsilon is like the I here. It's an index set, and each x it serves as an index, right? And the AI here is so just view everything inside. So to prove this one, we need to note the fact if the max, so view this everything inside the absolute value at just one object. If max of this object over this index set is greater enough to delta, then it's equivalent to say that there is at least one element is greater enough to delta. And with this observation together with the union bound, you can show this probability, which is pretty much like this one, should be less than or equal to the summation over the index set. You need some thinking here. But just basically the two facts. The max is greater enough to something, then at least one element should be greater enough to this delta. And then use union bound, you can prove this inequality. But here, the key thing is that we do not change this index set. Here is x epsilon, here is also x epsilon. But here, in the last statement, it's different. Here is max over x, right? This infinite many set, right? But we turn it to something finite many. That's the key difference here. But here we need a stronger assumption. We need to assume this mapping from x. So if you fix C from x to this stochastic function f of x comma C, this, if you assume this is ambiguous continuous function for almost every C, then you can prove this claim. So you turn this infinite many index set to this finite many index set. Suppose domain of H is bounded. So this is the final claim we are going to make. So then, because previously when we used whole-field inequality, it's just for one point. But here this is max for all the points, right? For any point x in the domain of H, this is what we care about in stochastic optimization. And this is your SAA, this is SO. So this is saying for any point x in domain of H. So right then the SAA will be so SAA and the SO, the difference between the two, if it's greater than or equal to this threshold, this is bounded by this probability. And to bound this one, you can use whole-field inequality to apply on this one. Because right, this is summation over all x in x epsilon. For any one, for any fixed x, for the one in the summation, you can apply whole-field inequality to bound it, right? This is going to be upper bounded by summation exponential minus 2nt some b minus a. But this b minus a, you need to find it because this is not given. B minus a basically gives you the diameter of your domain of H, right? But to bound each individual one in this summation, you need to use the whole-field inequality. And this decreases exponentially fast as the number of samples. Right? Combining whole-field inequality and this one together, you have the final conclusion that your SAA is close enough to SO if n is large.
So would that summation result in the covering number times that exponential? Because that it doesn't seem like the exponential has internal dependence on.
Right. That's right.
Okay.
Yes. Yeah, you can upper bound it. Yeah. That's right. You can just do the product. And this T is actually this delta. Right. So you just need to combine the two together to get the final conclusion. So the final conclusion is just that SA is close enough to SO as n is large, but and also it goes to that this probability goes to 0 as exponentially fast. Okay, so that's a quick introduction to SA. Now let's move on to SAA, which is closer to what we covered previously, similar to iterative methods in optimization.
I have a question. Like at the very beginning, we parameterize these two distributions.
Right.
How do you usually do that? I mean, if you have a density, you can parameterize the parameter of the distribution. But if you don't know what the distribution is, how do you parameterize it?
Yeah, that's right. So, for example, you can parameterize the distribution as a Gaussian mixture.
Okay.
Right, that's one typical way.
Okay.
Right, you can assume there are maybe 10 Gaussians, but you don't know really how many there are. This may not be really a Gaussian distribution, a Gaussian mixture, but you can use a Gaussian mixture to approximate it. Right, and you can assume there are, for example, you can assume there are many m Gaussian distributions, and it's a sum of m components. And for each one, you have this sigma I. You also have this mean value, maybe some AI. Right. These are the parameters you need in your zeta 0.
What is this used for? What is this used for?
It's just this note when A is compact, which is that domain of H. When it's bounded, then the cardinal number is finite, which is the cardinality of this A epsilon. A epsilon is X epsilon here, because we need this to be finitely many.
But A epsilon is a set.
Yeah, the cardinality, the number of members is finite many.
I know, but A epsilon is set if X epsilon is a set.
Yes, it's a set. It's right here. It's a subset of domain of H.
Okay.
Just some representative elements. right? All the other points are normal within a distance of epsilon. It's in a ball, epsilon ball from the members in X epsilon. Right, so that we can use X epsilon to replace X, but it's finite many. Then we can do the sum there. Right. Anyway, in the end, we don't want this summation to be greater than 1. Otherwise, this is meaningless, this bound, right? In SAA, let's make some more concrete assumptions to do the optimization analysis. So we first assume both F and H are closed and convex, and we also here we don't need to H is bounded. Domain for H is bounded. It's not like in SA. We don't need to assume domain for H is bounded, just closed. And we assume there are two oracles. Given X and C, we can take the stochastic function. We have this stochastic function value oracle f of x c, but in the algorithm we don't need it. And we also assume the availability of stochastic subgradient oracle. Given x and c, we can evaluate the stochastic subgradient s of x c. And they are both unbiased, meaning that if you take expectation over c for the stochastic function value oracle, this returns you the f of x. This is unbiased. There's no other error, right? It's unbiased. And also for the subgradient, if you take the expectation of the stochastic subgradient oracle for fixed x over c, then this is equal to the subgradient to f, which is f prime x. And we also assume some bounded variance for the stochastic subgradient oracle. So this is your stochastic subgradient oracle. This is the expectation, right? And if I take the difference and then take the norm square, and after expectation, this is like represents the variance of this oracle, right? And we assume this variance is uniformly bounded by sigma square for any x. If this is if this is deterministic, this sigma is 0. But here in the stochastic setting, we allow some variance, but it's always bounded, uniformly bounded for any point x. And we also need some smoothness assumption. And here I make it more general. Basically, this is f minus its linearization. In the smooth setting, you can view this m at 0. It's bounded by a quadratic term, right? That's a smoothness assumption. Then f is L smooth, or the gradient of is L Lipschitz continuous. And this basically is a Bregman divergence. It's upper bounded by just this term, the quadratic term. Or if the function is f itself is Lipschitz continuous, but not a subgradient. If it's Lipschitz continuous, which is a nice smooth case, then you can view this L as 0. It's just bounded by this first order term, right? So this is like a mixture of smooth condition and non-smoothness. So then we can give a unified analysis for both smooth and non-smooth. If you want to recover one of them, then just take the other one at 0, the other parameter at 0, right? This just generalizes the smoothness and non-smooth condition by putting them together. But here we do not assume any strong convexity. You can also do analysis for strongly convex case, but for simplicity, we just assume both f and h are convex, no mu, no strong convexity. Okay, and let's try to analyze the simplest algorithm, which is similar to that SGD, but we just replace the gradient by subgradient because here we also have non-smooth component. So in the algorithm, in every step, we just first choose a subsize between 0 and 1 over 2L. This comes with a, so this comes from the proof. We need to guarantee 2 times lambda L to be at least, at most of 1. This comes from the proof. And then we need to generate a stochastic subgradient. So xk is given, right? Xk is the iterate from the previous step. And this ck is what you need to take, and then evaluate this subgradient, stochastic subgradient. And then in the next step, this is similar to what we had before. Take a linearization, and then add a component, the composite function, and add a quadratic term. But here we replace, in the what matters in the linearization is the inner product, right? Here we're ignoring all these other constant, but we replace the subgradient by this stochastic subgradient. Usually we just use a subgradient, but here we just replace by the stochastic one, right? This algorithm is nothing but like the proximal subgradient method, but it's just the proximal stochastic subgradient method. Okay.
How do we generate that?
That's an oracle. We assume it's an oracle. It's available to the user. In the algorithm, we do not do anything more. It's just some oracle available to the user. But in practice, you need to have the ability to really implement this oracle. It may be taken as simple as some, but this is not realistic. Supposing you already know this expectation, and then just add some noise, maybe some WK, and WK maybe some follows a Gaussian distribution. But this is just an example. It may not be realistic. Suppose this X is something you can observe from the environment, but what environment provides you is something noisy, and you don't know the level of your noise.
Can we somehow sample from, use that sampling techniques for that generation of SASK?
That machinery is too heavy here. Just assume this is available to you. You can observe from the environment. And in the algorithm, just take this observation and do not do anything more. But it depends on the application. So with this algorithm, we can show, we can accomplish two objectives. First, we can show convergence in expectation that is similar to the result we have seen for randomized block learning descent. Because the difference is that in that problem, in that case, the problem is deterministic, but we randomize the algorithm so that in the end you can show something in expectation. But here the algorithm is deterministic. You do not do anything more, but the problem is stochastic. So you can only observe a stochastic subgradient. And then because of this randomness, so in the end, the result is still something like convergence in expectation. And beyond that, we can also show convergence in probability. We can show a high probability result that is better than convergence in expectation, because convergence expectation is just like a point estimate. But with probability guarantee, you can also conclude something like, for example, the confidence interval. You can say something more statistically, right? And I think I will stop here. Next time we are going to talk about the convergence analysis. Epsilon is the set of all the lattice points. So it's bounded. If A is bounded, then the length of A divided by epsilon is always bounded. Right?
So I had one question related to that. So the covering number for A epsilon, is that proportional to the Lebesgue measure of the underlying set?
Yep.
Okay, that would make sense. Then I'll let other people go first. I had a question about project.
I also
Oh, okay.
yeah, that's also so I didn't find the feedback.
But I can see it on my side.
Did you get feedback from
Yeah, I just got a quick feedback of, yeah, I think it was like one sentence, but yeah, I got feedback. I didn't know if there was supposed to be more involved or not. But.
Did you see the feedback from the people?
Yeah, you were. I thought yours. This is
Oh,
yours.
okay.
I just put it in a chat box.
Okay.
There's a chat box behind it. You can find it behind.
Oh, there's another chat box? Okay.
But you can see the feedback.
Yeah,
Yeah.
Actually, folks, I wanted to ask a question about my projects. As far as you're writing my report and
I should please.
we'll just.
I'm not sure.
I'm completely considering a field of non-time-based transition, and I'm writing a survey about it. That will consist of 3 or 4 papers, and I'm explaining all of
Because I see this, yeah, so I see this.
You see this. Okay, I see that. I
So
don't
if I click on the chat bubble,
Oh yeah, I don't have
then I
that.
see that.
Okay, well,
Maybe you don't have feedback.
yeah, I don't have feedback.
So maybe you don't, yeah, maybe it's perfect, sometimes nothing to comment.
Alright, thank you.
I had one question. So I had a plan of what I wanted to do. So I wanted to combine 2 methods with stochastic gradient legend and dynamics. Lo and behold, it turns out I got scooped. There's already an algorithm called stochastic gradient Hamiltonian Monte Carlo that people have done replication with. It also has momentum. So that already exists. And also I've realized since then, so I previously had been using legend dynamics for optimization, but it's more suited for sampling. Would it be acceptable for me to test adding momentum to stochastic gradient legend dynamics for sampling? And for instance, minimizing the Wasserstein distance, or just because I wish I had had time to work on this earlier.
So you wanted to design some new algorithm?
That was my plan.
But you figure out it has been tried.
Yes, yes, it already exists, unfortunately. That was my plan, or not necessarily even design a new one. It was basically just seeing that there were 2 ideas that could improve performance and combining the 2, and then potentially deriving some interesting result, and then doing some experiments with it. But
You can try some implementation and just have an initial idea of something new.
well,
It doesn't have to be complete.
well, the problem is that people have kind of already done it before. Is my point. So
Or we can
basically,
do
is that
like a survey to summarize the ideas.
okay? So I can
You can do like a survey or implementation.
Okay.
Both are okay.
I will do it, because I was starting to panic a little bit because I didn't have time to come up with another new idea.
It could be too optimistic to design algorithm.
I figured I just hadn't seen that done before, and it's because it was a different name. I was looking for legend dynamics, and it was called Hamiltonian Monte Carlo. So that was what was throwing me off. Okay, thank you.
Sure.
塞的方法，就是而且是个求解器。就是如果比如说我现在有一个微博的01转速规划，
Groovy。
用 Groovy 可以做出来。比如说我有上亿条的。
那你要不要先那个 reduce 一下你的 constraints， 有一些什么这些就是 linear dependent。
Hey Joe, sorry I meant to check in on you.
Yeah. I'm all right. It's been sick on and off for like a while.
Wow.
Ever since it started getting cold.
Excuse me?
Ever since it started getting